In this video, I want to do a dehumidification problem. This is very similar to what happens in air conditioning systems. I'll explain the slight difference, but this is a dehumidifier, and what happens is we have moist air coming in at a relatively high temperature and high relative humidity. It enters at a certain flow rate. The condensate that is obtained from the air passing over a cooling coil is collected and removed, and the moist air leaves at 10 degrees Celsius at 100% relative humidity. It's saturated air after losing the various amount of condensate. And so the pressure remains at 100 kPa, that's the pressure through the system, and we want to know the mass flow rate of the dry air. We want to know the water removal rate between state 1 and state 2. It's coming out here through the condensate removal pan, and we also want to know the required refrigeration capacity required in order to perform this dehumidification. So let's go ahead and this particular problem, we're going to go to our test app. And again, this is a psychometric problem dealing with the flowing system. And so we're going to select this particular test app. As we indicated on this problem, we have our pressure is at 100 kPa. That is the pressure for the moist air. The moist air we determine is coming in at 40 degrees and a relative humidity of 90%. And our mass or volume flow rate is in meters cubed per minute, as given in the problem, is at 300. And so with that in mind, what we have determined then is at this relative humidity, at this particular temperature, we have a mass of dry air that is 311. In addition to that dry air, we have this amount of vapor. And so this plus the mass of dry air is the total that's flowing through the system. And so we have our first state. We now will go to our second state. The second state is at a pressure that's equal to the same pressure 1. We are told that we bring the fluid, the moist air, down to a temperature of 10 degrees, and it is saturated, 100% relative humidity. What we know in this particular case is constant is the mass of the m dot of the dry air. And so the mass flow rate of the dry air is constant. It's not the volume flow rate. Okay, the mass flow rate now, as you can see, because of this lower temperature, is now down to 2.4. So that is the flow rate of the vapor associated with this new condition at 10 degrees Celsius and 100% relative humidity. So we have state 1 and we have state 2. So at this particular time, we could very easily have just taken this 13.8, which is the mass flow rate of kilograms per minute of the vapor, and subtracted the 2.40 kilograms per minute to obtain the answer, the water removal rate. We already know the mass of the dry air, so we've answered problem 1 and we've answered problem 2, or A and B. And now we're looking for what is the refrigeration capacity. How much heat did we have to remove from the moist air in order to affect this new condition? So with that in mind, we need to now set up a state 3, and our state 3 is going to be the water itself, and so it's the condensate. And so we select under the various components, we select H2O phase change. And so it's water and not moist air mixture. And so we select that. We know it is told to us that the outgoing temperature of the water is 10 degrees, which is the same as the outgoing temperature of the air, the moist air. And we also can put in that the m dot 3, or the mass flow rate of this particular stream, is the m dot of the vapor minus the m dot of the vapor at 2. And so that's where we take our 13 minus 2 something and get, so we now know the mass flow rate of the water in kilograms per second. Okay, it will keep everything consistent in terms of values. If we wanted to know the mass flow rate of water in the same condition, we'd want to put it into kilograms per second. But again, we will see that on the output page for the answer. And so now that we have state 1, state 2, and state 3, we can now go to the device panel. And on our device panel, we come in at state 1. That's the only thing coming in. We leave at state 2. That's the moist air, but then we are also leaving with state 3, which is water, liquid water. And so it knows these conditions. It also knows the flow rates. And so we say that there's no heat transfer. And so we see in this particular case that the heat transfer required for this refrigeration process is 639 kilowatts, but we can switch that over to tons of refrigeration and get 181.9. So a ton of refrigeration is 12,000 BTU per hour rate, and so it is can be obtained from the kilowatts, and so it's about a 3-to-1 difference there, 3 to 4 to 1, 4 to 1. And so we have the answer to the problem. The answer is 181.9 tons of refrigeration. Now, if we were to put that on our graphics panel, we see that our state 1 is up here at an elevated value of the humidity ratio. It's also at an elevated temperature of 40 degrees Celsius. State 2, as we said, was saturated, so it's on the 100% relative humidity line. It's at a much lower omega, and we see that the temperature is 10 degrees Celsius. And so the process was going from here down to here. Now we know from the psychometric chart that there is a scale that corresponds to the enthalpy that runs at a diagonal. And so the enthalpy we would obtain for state 1 would be picked up and subtract, and we would subtract from that value the enthalpy for state 2. And the difference between those two then is the refrigeration effect. Now in heat transfer, in HVAC applications, that is very well to know that particular value, but usually what happens is it's broken into 2 different components, because what's actually happening is we go from this condition here and we remove the water and then we cool the moist air down. And so what typically happens is one looks at this as a two-step process. We go from state 1 to a state, and let's call it state 4, where we only change the humidity ratio, but keep the temperature the same. And then we come from that particular condition over to here, where we then cool the mixture down. And so in order to do that, I'm going to go back to my state panel. I'm going to select a state 4, which is moist air. And for state 4, I'm going to say that the pressure is P1. And I know that for that condition, the temperature stays the same. It's at temperature 1. So I'm going straight down in an isothermal fashion. And what I'm doing is I also have my m dot air is the same. And what else I know is I know that my my final volume of vapor is equal to m dot vapor 2. And so I've come down to the new value of the humidity ratio, a new amount of the omega. And so upon doing that, then I have this state 4. And that state 4 is right there. And now what I want to do is I want to go to my device panel. I'm going to select a device panel that is from 1 to now 4 and 3. And so I want to take out, I want to go to state 4, but I also want to take out the liquid water. And so with this and with no work, I then see my heat transfer is this, and in tons of refrigeration, it's 136, as to compare to the total of 181. Okay, so now I'm going to go and I'm going to add my second step. And my second step then was to go from state 4 to state 2. Okay, again, I've already gotten my moisture out of there, so I don't have to take the moisture out. I'm going to go from 0 here, and I then have a heat transfer that I turn into tons. And so now you see what has happened is the second step required 45 tons. The first step required 136 tons, and the total required 181 tons. Okay, this term here is called the latent heat, because it has to do with the latent heat of the water that has to be removed in order for condensation to occur. And this term here, which is just the heating of the moist air mixture, or the cooling in this case, this is called the sensible heat. And so the sensible plus the latent equals the total. And again, it corresponds to the fraction as we take the process from state 1 to state 2. It is how much is required to get to this point, and then how much is required then to get to the final point. And so that's of interest because when we look at psych charts, and I'm going to go ahead and bring up a psych chart real quickly here that I have. Oops. Okay, I want to pick up my head. Okay, and it's on my desktop here, so I'm going to open. Okay, my mistake here. Let me open. Okay, this is the psych chart that I've put on Blackboard for you. And so in this problem that we just did, we started at the 90% relative humidity line for a temperature of 40. And these are kind of hard to read, but the 40 degrees, that's 20, 30, 40. Here's 40 here. So we started that process actually off of the chart. We were way up here. And then we came down to 10 degrees, 100% relative humidity to this point right here. And so what we proposed is that we had two processes. One that came down to a lower amount of the relative of the humidity ratio, and then one that went over. And in each case, we came over and we picked up an enthalpy of the moist air mixture over on this chart. And we saw that the first case went down and we took the difference and we had the latent heat. And then we had the sensible heat. Now, if you take the sensible heat and divide it by the total, so the sensible heat was 45, and you divide it by the 181, you get a ratio. And that ratio is called the sensible to total heat ratio. And so that would have been, in our particular case, 45 divided by 181, about a quarter. And so if you were to go to 2.5 right here, 0.25, that corresponds, to a, well, let's see, it'd be this one right here, 0.25. That corresponds to a angle, okay? And basically that particular line there would correspond to the line between the starting point and the finishing point. There's a slope there, and that slope is the ratio of 0.25. And so if you had a straight edge and this protractor, you could start at this point and you could then obtain the slope of that process line that corresponded to 25% of the heat transfer was sensible and 75% was the latent component. And so these are some of the things and why you see certain types of things showing up on a psych chart, these protractors and other things like that.